Hello student, myself Nimesh Prabhakar. Welcome to Process Control lecture series. In my previous lecture, I complete chapter number 4. So in this lecture, we start new chapter number 5. In this chapter, we discuss about the different type of controlling modes like P controller, D controller, PID controller. So in this lecture, we discuss about the controller modes, then we discuss about the process leg, then we discuss about the errors, and last we discuss about the control leg. So without wasting time, now we start. So first one question come in our mind, what is controller modes? So the answer is controller mode refer to the methods to generate different type of control signal to final control element to control the process variable. Now we discuss about the classification of different controller modes. So mainly it divides into 3 types. So first one is classification based on discontinuous control mode. So in this, first one type is 2-position control mode, or is also known as on-off controller. Now second one type is multi-position modes, and third one type is floating control mode, like a single speed and multi-speed. Now next one type is continuous control mode. Now it also further divides. So first one type of continuous control mode is proportional control mode, second one is integral control mode, and third one is derivative control mode. And third one, classification based on composite control mode. So this is also further classified. So first one type is proportional plus integral control mode, or is also known as PI mode. Now second one is proportional plus derivative control mode and is known as the PD modes, and last one type is proportional, integral and derivative control mode. It's known as the PID controller. So this is the classification of the control modes. Now based on the controller action on the control element, there are 2 modes. First one is direct action. So what is direct action mode? Now we see. If the controller output increase with increase in a control variable, then it is called direct action. Now we understand by help of this example. In level control system, if level rise, that means increase, then the value should be open. So then the valve should be open. That means drive signal should be increased. We know level control system. So in that level control system, if we that means the flow is increased. So at that time we have to open the valve. So at that time we also increase the controller output. That means this type of controlling action is called as a direct action. Now we discuss about the second one type of controlling action. So second one type is a reverse action. As name indicates, you can understand reverse. That means opposite of the direct action. If the controller output decrease with increased controller value, then it is called reverse action. Now we understand by help of one example. In the simple temperature control from a heater, if the temperature increase, the drive to the heater should be decreased. So this is the example of reverse action. Now we discuss about the controller modes. The choice operating mode for any given process control system is complicated decision. We all know. It involves not only process characteristics but cost analysis, product rate, and other industrial factors. The process control technologies should have good understanding of the operational mechanism of each mode and its advantage and disadvantage. In general, the controller operation for the error EP is expressed as P is equals to FEP. Here, FEP represents the relation by which the appropriate controller output is determined. Now we discuss about the process leg. So first one question comes in our mind, what is process leg? Why we need to study this process leg? So now we discuss. A process load change or transient cause a change in a control variable. That means in a process there is something changed in a load, or we can say as a process load is changed. So at that time controlling variable is also changed. The process control loop responds to ensure that some finite time later the variable returns to the set point value. Part of this time is consumed by the process itself and is called process lag. So this is the process lag. Now we understand proper by help of this example. You can see this is a system in which we give the inlet flow. That means we give the in the input side we give the cold water, and by help of this second one phenomena we increase the temperature, and the output side we get the hot water. Assume the inlet flow is suddenly double. That means here this is the inlet flow is double. A large process load changes radically, reduce the liquid temperature. That means if suddenly we increase the inlet flow, so at that time temperature is also vary, or that means temperature is reduced inside this tank. So the control loop responds by opening the steam inlet valve to allow more steam and heat input to bring the liquid temperature back to the set point. The physical opening of the control valve is slowest part of the process. That means if we open the control valve, at the same time we cannot get the result. That means at the same time temperature is not increased at desired value. So this is some type of delay is occurred, and this delay is known as the process lag. Now we discuss about the another error. Error is the difference between the measure variable and the set point. So this is the general definition of error. Error can be either positive or negative. The objective of any control scheme is to minimize or eliminate the error. The deviation of error of a dynamic variable from set point is given by E is equals to R minus B. Here E indicates the error, B indicates indicate the measure indication of variable and R indicate the set point of variable, that means reference point. To describe controller operation in general way, it is better to express the error as present as percent of the measure variable range or the span. So the measure value of the variable can be expressed as percent of span or the percentage of span over a range of measurement by the equation. So this is the equation. Cp is equals to C minus C minimum upon C maximum minus C minimum into 100. Here Cp indicate measure value as percent of measurement range. C indicate actual measure value. C maximum indicate maximum of measure value. And last C minimum indicate the minimum of measure value. Now we can express the error as percentage of span. By using this equation, we can express the error as a percentage of span. That means EP is equals to R minus B upon B maximum minus B minimum into 100. So here EP indicates the error expressed as percentage of span and B maximum indicates the maximum value of measure indication of variable and B minimum indicates the minimum value of measure indication of the variable and R indicates the set point of the variable or the reference point. Now we take one example for the error calculation. So this is the figure of this example. So here the temperature in figure has a range of 300 to 400 Kelvin and a set point of 384 Kelvin. Find the percent of span error when the temperature is 379 Kelvin. So here we have to calculate the percent of span. So now in the example we have given R is equals to 384 and P is equal to 379 and B maximum is equals to 440 and B minimum is equals to 300. So we can calculate the percent of span by using this equation. EP is equals to R minus B upon B maximum minus B minimum into 100. Now we substitute the value of R, B, B maximum and B. So we get EP is equals to 3.6%. Now we discuss about the variable range. Control variable has a range of value within which controller is required to be maintained at set point. This range can be expressed as the minimum and maximum value of the dynamic variable. Like we understand by help of this example. If a standard signal 4 to 20 milliampere transmission is employed, then 4 milliampere represent the minimum value of the variable and 20 milliampere represent the maximum value. So this is indicate the variable range or the range of variable. Now we discuss about control parameter or the output range. In previous slide we discussed about the control. In the previous slide we discussed about the variable range. Now in this slide we discussed about the control parameter range. It is possible range of value of final control element. The control output is expressed as a percentage where minimum control output is 0% and maximum controller is 100%. So this 0% and 100%, this indicate the range of the output or the controller output range. But actually 0% controller output does not mean zero output. For example, it is necessary to requirement of the system that a steam flow correspond to a one-port opening of valve. That means if we say there is a 0% output, that means in the practical it is not possible that 0% is controller output. We give some amount of output. The controller parameter output as a percent of the full scale. When the output changes within the specified limit is expressed as P is equals to U minus U minimum upon U max minus U min into 100. Here P indicates the controller output as percent of full scale. U indicate the value of output. U maximum indicate the maximum value of control parameter, and U minimum indicate the minimum value of control parameter. Now we discuss about the example. Here a controller output a 4 to 20 milliampere signal to control motor speed from 140 to 600 rpm with a linear dependence. Calculate first one, current corresponding to 310 rpm and the value of A expressed as a percent of control out. So here we have to calculate the current. So now we start procedure. We find the slope M and insert S0 of the linear relation between the current I and speed S. So now here we start procedure to find the value of current. So by using the algebraic equation or mathematical equation, we solve this example. We know this is a linear line equation. Sp is equals to ml plus S0. So here the Sp and the I at the two given position, we write two equations. So to find out the S0, so by using the given data, we know the 140 is the minimum value of the Sp is equal to, at that time the minimum level of current is 4 milliampere. So we write 4 into M plus S. And we can also write second one equation like 600 is equal to 20 M plus S. So here we have two equations. So now we can find the value of current. So solving this simulation equation, we get M is equal to 28.75 rpm per milliampere and S0 we get the 25 rpm. So now we substituting this value in the first one equation. Thus we get at the 310 rpm we have 310 is equal to 28.75 I plus 25. So we get I is equal to 9.91 milliampere. Expressed as a percentage of the 40 to 20 milliampere range, this control output is P equals to U minus U minimum upon U maximum minus U minimum into 100. So we can get P is equals to P is equals to 36.9%. So this is the percentage of. Now we discuss last one point, control length. control lag refers to the time for the process control loop to make necessary adjustment to the final control element. Now we discuss by help of this example. If sudden change in a liquid temperature occurs, it requires some finite time for the control system to physically activate the system control value. So that means if suddenly change in the temperature, then controller requires some time to take controlling action. So this time delay is known as the control lag. Now in this lecture we discuss control modes, process lag, error and control element. Thank you.